Before we get rolling, Dr. Shep, what can we expect? Like, what are we? Is it literally just this homework and that's it?
Yeah. Basically, I mean, obviously there's going to be different problems, but
Yeah.
it's the topics, right? The filtration and the. Yeah, well, I'll talk about that in a second.
All right.
It's good.
It can't be the same. Because then, how did you learn anything? You learned how to regurgitate. That's the same exact problem.
My parents told us
I'd say that's it. As an engineer, you're supposed to come up with ideas.
How can you be a problem solver if it's not a problem to solve it? You're supposed to have trouble. Okay. All right, everybody. So before class, I had a couple questions here. One about the exam date, and the other about what to expect from the exam. And so I want to talk about both of those things real quick. I also took a couple minutes before starting to make a Kahoot to get your feedback on how you would feel about changing the date for exam number 2. So as promised, if you warn me ahead of time, I'm willing to bring it up to the class to see if it's worth moving the exam for you. We're still a week or two out, or I guess 2 weeks out. So I'm willing to do so. And the deal is we could take the Flint water crisis lecture session and move that to be after exam 1. That really wouldn't affect your process at all, I don't think. If we did move the exam forward in that manner, I would probably also have to then move the exam review forward and move your homework due date forward. But since I'm not collecting the homework for grade, just for completion, I don't think I would mind too much. First of all, I don't think you would mind or be disrupted too much by that. I also wouldn't mind just taking it a little later if needed. But for your benefit, I think it's best if you have the homework done before the exam review. Okay, so having said that, one option is to move the exam number 2 forward. Otherwise, we can possibly push it back and have an intro to wastewater before the first or the second exam. That's another topical session, so we do have some flexibility there in terms of kind of quantitative meat and potatoes calculation sort of stuff that we're going to deal with. That's going to put you 2 qualitative lectures before the exam, so it might be a little while since actually in class looking at equations and doing example problems and stuff. So maybe that's not ideal, but I'm open to it. So what I'll do is start off with a Kahoot about that to get your, basically it'll be one question. It's just asking, okay, how do you feel about moving it? And one answer will be like, yes, anything but the current schedule is great. The other would be yes, but it has to be a specific date, and I can talk with you about that later. Or probably rather not, or definitely rather not. So those will be the options. As far as what to expect on our second exam, really it's going to be all the filtration and all the disinfection. And with the disinfection, we're kind of revisiting, in a sense, the chlorine and equilibrium chemistry a bit. So it's going to be a little bit of chemistry in that sense to be able to handle chlorination as a pH-dependent process. But otherwise, it should be pretty straightforward with the filtration, disinfection, and that'll kind of be it. So it's not as comprehensive, I suppose, for the second exam. All right, with that, let me bring over the Kahoot.
Yeah.
Yeah, and please do sign in with your 8-9 number so that to take this as a.
I literally just tell the professor, there's no way I'm remembering this. Let me bring my wallet so I can pull out my card. Oh, Jesus. I'll be looking at everything. You know, yeah. You know, like America exclusive almost.
All right, anybody else need a moment? All right, here we go. Do we have music this time?
I appreciate the time that we get for this question. It's not like 15 seconds. Yeah.
A little less stressful.
I do that. So I'm going to say I'd rather not. Well, some
I can take it.
Can I open my vote? If that makes sense?
Huh?
The data bit doesn't matter, regardless, it's going to suck. So,
If I needed a fifth option, it's like none of the above.
Yeah.
I don't like exams.
well, every weekend next month I'm going to be out of town. I've got a wedding and a bunch of other stuff to plan and set up for other people.
Let's
I'm
put.
not getting married, but yeah.
Who's getting married, guys?
No.
My,
Not
my,
a chance.
I was supposed to go to Florida this weekend for my cousin's wedding, but Ida came through and sort of wiped out the wedding venue. So there's no longer an island there, I think, is what I heard.
Yeah, right.
So that was canceled. All right. Okay, so nobody's in the absolutely not. Maybe, depending on how I counted, about a third of the class, rather it not be moved. So if I move it, I will make that announcement very quickly. Some of you really would need a specific date. So looking at the dates real quick, verbally, which dates is the specific date? Is it the first? Anybody? It's like must be the first.
Oh, no. Some people are also dependent on professors because they don't announce their exam date until like
Right.
2 days before.
Yeah.
Not
And-
mentioning any names, Dr. Son, but it does happen.
Okay, so how about the 8th? If it's moved and whoever marked it must be that few of you. Okay, so no, what I'm saying is like if you answered the one that's like, oh, if you move it, it must be a specific date. So I was checking those two to see if that was, but it sounds like that to move it back is the kind of the only option. All right, I will think on that. If you get any new revised information about that other exam, it becomes more or less of an issue, please do let me know. And also, if you have some serious concerns, like you'd rather it not, but you're kind of on the verge, like let me know if there's something that's really seriously going to be a problem if it does get moved, even if you didn't mark absolutely not. So email me about it if you have some more information one way or the other, and I'll think about pushing it back one class period.
Could we do it on not a Monday, like on Wednesday? Just so we can do the.
It's going to be in class on a Tuesday or Thursday.
Oh, never mind. We're good.
Okay. All right. Thank you for the feedback.
What is happening to
All right. So, last time we worked this problem, computer crashed in the middle of it, but we kind of redid it a little bit. So we worked through this kind of HOCl, LCl minus, equilibrium reaction, figure out how much stuff we had there. So this time, what I would like to do is continue on. In fact, I think we got to this slide talking about disinfection byproducts. So what I'd like to do is kind of continue on with chlorination a little bit, start talking about how we quantify the rate at which a disinfectant is going to work. And we'll also use that same concept to take a look at ultraviolet light disinfection. And that'll kind of be the majority of what I want to cover for disinfection in particular. I might take another extra class period. I'll have to go back and check to go a little bit more in depth on UV disinfection based on some of our ongoing research, sort of more of a special topics type of a deal. But today should get us most of the way through disinfection. Okay, so when we want to quantify how fast is the chlorine going to work, just like in other cases we wanted to know how fast are the particles going to stick together during coagulation, flocculation, well, it's going to come down to a mass balance, and we want to know the components that go into the rate at which the pathogens are going to be killed. Okay, so for this, we're going to use what we call the CT concept will come into play. That means that for any given concentration, you're going to need to expose it to the pathogens for a certain amount of time. So if you have a high concentration, it's going to be short time. Low concentration, high amount of time. But those two, the product of those two, so the combination of concentration multiplied by time, gives you a value where you should be able to kill 99.9% or whatever, right? So that gives us a nice handle that accounts for both. This is that CT concept. It's often called contact time. You can also understand it as concentration times time. Because that's literally what it is, giving us some estimate of how much contact did the pathogen have with this disinfectant. Okay, and we could call a dosage. So that's sort of a general concept, and we'll see it play out in our rate equations here. For the rate itself, we understand based on some early work in the field by, reported in a study by somebody, Chick and Watson, I guess two authors probably, and they put forward this kinetic model that said it's basically first order reaction. So you might call it pseudo first order. And so we can essentially treat it like a first order reaction for all intents and purposes, but there's maybe some assumption involved. And that assumption would come into the play in terms of how well mixed the reactor is and what we know about the concentration that's in it for our disinfectant. So that's called Chick-Watson kinetics. Again, pseudo first order, and this is going to be decay because we're killing the microbes, presumably. And that means we're going to have, if we look at dN dt, where N is our microbe concentration, then we can set that equal to negative K times C to the N power times N to the 1 power. So this is 1 because it's first order. We're looking at dN, how N is changing. So the fact that we have a C and an N can get confusing because a lot of the mass balances we've done have been either C or N, right? Some concentration, so we use C. Or N for a number of organisms or particles or something, right? So given that we're doing this as N changes, that's the differential equation is dN, then what we're looking at then is the rate at which N is changing, not C. C is our concentration of disinfectant, okay? And that's defined right here. So C being our concentration of chlorine or ozone or whatever we're using, could be, just as an example, could be milligrams per liter, millimoles per liter, whatever it is that we're using. That's the concentration of the chlorine. And one of the reasons we're saying this is pseudo first order is because normally that stays constant. So right down here, it kind of mentions that C is constant, gives us that first order decay. Because if C is changing, especially based on reaction with the pathogens or whatever, then we're no longer first order in our kinetics. The way N is going to change over time is going to depend on two different things that are changing over time. It gets complicated, and it's essentially second order or similar. Maybe it's somewhere between first and second order. So we're going to simplify and make the assumption that, which is generally valid. Of course, we solved a problem earlier this term in class about ozone decaying through a pipe over time. So in certain situations, it's not true. And maybe to simplify that pipe case, maybe we would just say, let's just assume it's getting the minimum value the whole time. It's going to be better than that, but at least we have a safeguard, right? A safe minimum to deal with. So maybe you could simplify in that manner and design a system. Yeah, you'll have a tiny bit of extra cost because you could have done fancy math, but who wants fancy math, right? I was actually just in just yesterday serving as a what's called a dean's representative for a PhD committee exam for a mathematics student, and it was just everything's like, phew. It's like pure math. And then I got to the end, I was like, okay, so how does this matter in real life? It's like, so it was just very interesting, the engineering versus the mathematics perspectives there. From what I could follow, it was an interesting study, and they were doing had to derive new math for what they wanted to do. So it was very interesting, but also very, very fancy math. Okay, anyway, this n here, this exponent, it's going to be a constant. This is going to be normally just 1 for us, but this is where the other aspect of the assumptions come into play. We assume that, we assume that C is constant, and then the n can account for if the chlorine is actually well mixed throughout your system, right? Because if you have an uneven mixture, and in one side of your reactor, you're putting in the chlorine and it's high concentration over there, and then it's just not properly mixed. It's, we're calling this a dilution coefficient. If that chlorine is not diluted through the entire system, but perhaps only makes its way through about 90%, then that would be a 0.9 dilution factor. Essentially, that's going to reduce the effective amount of chlorine because it's not contacting some of the pathogens. So that's a coefficient that we could easily add in there. That's not going to change the reaction order because C itself is not, the thing that's reacting. But we could do that for non-ideal reactors if we wanted to account for them. So assuming it's an ideal reactor, that whole equation just becomes dN dt equals negative KCN, right? That's kind of the simplified form there, where this K is specific to whatever organism we are attacking with the disinfectant and the particular disinfectant we're using. Okay, so those are the other two notes here. This K is described as coefficient of specific lethality. And this is not our typical K in a sense where for a first order decay reaction, we expect K to be 1 over time, right? Repeated that over and over again. A first order reaction, units of K is going to be 1 over time. Well, it actually has to account for the C in there as well. So this is going to be 1 over concentration times 1 over time. So then if we put the C and the K together and call it K star, then we have the form we're very familiar with. dN dt equals K star, negative K star times N to the 1 power. That K will be in pers time, right? Because there's nothing else affecting the units. So we can combine the two and get this K star, and let's say that might be per minute. That would be fine. So in this case, we take liters per milligram times minute, multiply that by milligrams per liter, and we get per minutes out of that, right? So that would be the K times the C. Okay, so overall, it's very, very similar and actually quite simple. Like if you compare it to the flocculation equations, elaborate stuff we have to solve for to just find the K, ultimately we end up with 1/seconds in that case. For disinfectants, it's pretty straightforward, the concentration of your disinfectant and that coefficient of specific lethality, and the combination of the two give us a per time K star. Okay. The difficulty might be if we're using chlorine, that concentration is going to be pH dependent. So we could have a problem where you have to solve for the equilibrium reaction in order to get the appropriate concentration to go into your rate equation, right? Which is why we care about that equilibrium stuff in the first place. How do we know how much concentration we have of the good stuff, right? Of the stronger disinfectant. Okay, so that's the essence of quantifying in terms of disinfection potential. Now, just to elaborate a little bit on the coefficient of specific lethality, the K just by itself, we could take a look at all sorts of different data. It's a little bit from some of my past work. This data is using actually a photoactivated system to destroy this MS2 virus. It's a virus that infects bacteria. It's very handy to count them that way because you can let them infect the bacteria, then grow them in a day, rather than like some human cell that'll take weeks to grow enough to see if they died or whatever. And that way, the E. coli is cheap and easy and non-pathogenic strain. This virus doesn't infect humans or anything, so it's just a nice, easy way to count some viruses in a lab in a very quantitative manner. And this one, we're producing singlet oxygen. It's just like normal oxygen, except it's been excited. It's very energetic and likes to go react with things. So it'll go and destroy our virus and kill it. And there's a coefficient of specific lethality for that, right? So that's just kind of what we were showing here is like, it can happen very fast if we add a lot of this, essentially the stuff that produces singlet oxygen, or it'll slow down as we reduce the amount of it. So that's just an example. And what we can do with a plot like this is take a linearized approach, get the log or the natural log, to get that slope and see how quickly the thing is dying and calculate backwards to find our coefficient of specific lethality, if we were interested in that. So speaking of that, here's an example problem. And I asked my other class this when we covered this, how many of you could today take your a graphing calculator, if you have one, and generate a line of best fit through a bit of data like this? Anybody feel like you could do that right just today?
With Excel.
Yeah, so with Excel and maybe, hopefully you can do that in Excel. If not, maybe I'll give you some practice. So what was interesting to me is like, as I was reflecting on it, I remember in high school, I did a lot of that with the graphing calculator. I think in college, we sort of stopped and it was always just Excel if I was going to do it. And I was thinking to myself, when did I lose that? Because if you gave me a TI-83 today, I could probably figure it out before too long. But like at some point, my TI-83 broke, and the only thing left was I could find was a TI-89, and then I was like, okay, well, I'm sure I could learn that, but by then it was like hardly using it in college classes anymore. So it's just a weird thought to me. And then it's kind of funny to ask you guys because it's like I don't know where you're at, and I don't even know where I'd be at in a sense, right? So anyway, certainly a line of best fit. Hopefully you can do it with Excel. I'll show you that in a minute. But this problem here is asking for that. And in fact, there's probably a clever way to estimate it even without a graphing calculator. If you like were to plot them physically and then take a slope or take an average of the different slopes between the points or something, you could probably get a pretty good estimate without any regression analysis. Okay, so let me read the problem and give you a moment to think about what it would take to do the problem and see how far you can get. And then I will elaborate and bring up Excel to kind of go through a bit of a more formalized approach. Not something we would do directly on an exam, but the concepts here I think will be helpful to see it in practice. Okay, so here we have data for HOCl disinfection, that's the stronger one, of poliovirus at a concentration of 1.8 milligrams per liter, is shown below, adapted from a previous study. The temperature was 20 degrees Celsius, the pH was 6. Then it says determine the rate constant for inactivation using Chick-Watson model, assuming it applies with an n value of 1. So they have some sort of reactor, and with a system like this, they didn't really describe it much. They just said it was disinfected, and here's the numbers. So basically, we can assume this was in some sort of little batch container they were studying. And whenever we're doing kinetic analysis, it's pretty much always going to be batch because it's so simple. All right, so we have data for time and data for the number. And we're not even given really a number per liter or something, so we could just call it, we could just assume that's per milliliter or something and just call it N. Okay, so there's a couple pieces of information here, and we could interpret it in a way where we would give ourselves a lot more work. And I will make sure, if I give you a problem, to be clear about this more so than this problem does. So this says HOCl is disinfecting poliovirus at a concentration of 1.8 milligrams per liter. So we could think to ourselves that that means HOCl, the concentration of it, is 1.8 milligrams per liter. Notice I did not put that in brackets. Brackets are only for moles per liter, right? So I'm just going to say HOCl is equal to 1.8 milligrams per liter. That's kind of what it sounds like it's saying. But if we were to assume they just meant they added 1.8 milligrams per liter of some form of HOCl, then we have to decipher how much is HOCl versus how much is OCl minus. Okay, so for the scenario today, we'll make that assumption, but as a side note, if that's 1.8 milligrams per liter total chlorine, then we have to consider the Ka for chlorine, which is typically 10 to the negative 7.54. They give us temperature information, which equilibrium constants are technically temperature dependent, so that would give us something close to this. And that's for HOCl dissociation with OCl minus and H plus, right? So then we solve for HOCl. Well, first of all, we'd have to convert it from milligrams to moles. Milligrams per liter to moles per liter. Then fraction, we have to look at what fraction is in the HOCl form. Then we'd have to convert back, if we're going to deal with milligrams per liter units, we'd have to convert back to milligrams per liter. Given that HOCl and OCl minus are very close to the same molecular weight, in this particular case, it wouldn't matter a whole lot, I don't think. But anytime we're dealing with equilibrium reactions, we have to be dealing with molar units. It's by definition must be. So that's kind of a side note. We're going to assume in our case that the molar, well, not molar, sorry, the actual concentration, like we set up here, that it is 1.8. In part because I don't want to beat a dead horse, and we're just doing this problem essentially last time at the end of class, right? We didn't take it into a kinetic model, but we got pretty close. Okay, so take a minute, think about what you would do from here. If you have a laptop, feel free to get Excel. If you have a graphing calculator, feel free to play with that. And I'll give you 3 or 4 minutes to kind of look it over and think about your approach, and then I'll work through it with you.
is the first one that you said. This whole column is n, but this is the first n, so it's n not.
All right, so if you take a look at the problem, and first thing maybe you'll think about doing is just graphing the data. You could graph it as is, the number versus time, and it'll look something like this. And if you think about it, that should be exponential, because when we take a look at our rate equation, the dn dt, we really have to integrate this before we get like a true look at the picture. And so when we do that, you know, we call it a batch reactor. We put a V on both sides, which just cancel out, right? We integrate and we get our typical, and you know what? I'm just going to go ahead and say for the sake of brevity here, this K times C is equal to K star. Right? That just kind of puts it all into what we're normally used to dealing with. So just for the moment, we're going to say, we know that when we integrate this, we get essentially this form, n over n naught equals e to the minus K star times time, right? Or before we even quite get there, we could have left it as ln of n over n naught is equal to minus K star times time, right? That should be pretty familiar with the first order decay batch reactor system. Well, if we leave it in this natural log form, that actually becomes pretty convenient. And of course, we could write this as n equals n naught times e to the minus K star t. Or we could kind of do the same thing over here. But if we get it in this particular form, then it actually becomes pretty simple to solve for the K as a slope on a graph, essentially. So if we rearrange for K, say K is equal to, K star. K star is equal to negative natural log of n over n naught divided by time. That, if we were to plot the natural log versus time, the slope there of the result is going to be very, very convenient and give us exactly K star. So if I were to plot it this way, we get kind of a exponential. Then if I were to plot it as a natural log of n over n naught versus time, that becomes really, really useful. I think we may have mentioned this before, pretty sure we did. That should be essentially linear, okay? So that's what I'm going to do in Excel, or I've already done, and then you can do a line of best fit through that, which is not what I've drawn. Just gonna, you can just imagine a line through that because I'm not going to draw it. All right, so in fact, there's a couple of different things we can do with that. Right here, what I'll say is when I put in, we can ignore that. When I put in the time versus the number, I didn't even bother plotting that, but you saw I kind of did that by hand, and that was to scale enough so you could see the curve, right? That's going to be plotting it without what we would call linearizing it. That's just this raw number versus time. But then what you could do is you could calculate the n over n naught, where the n initial is that number we had at time 0, right? That's our n naught. And so what I've done here in this equation is that I've said, let's take the natural log of the current time period, whatever number we have at that current time, divided by the initial time. So in this case, I put a so that I could fill it down, I put a number, excuse me, a $sign in front of the 5 on the denominator. So then when I fill it downward, we can see that C5 stayed, that's our N naught, and it shifted the next one down for the next current time. Right? So now at time 2, I look across and this is my formula, and it's that value is negative 0.7, right? And so we can fill that all the way downward. It goes nice and smoothly. We get each of those values. That's a natural log of n over n naught, right? So that's a linear form now. So we can plot that versus time over here, and our dots will come out like that. And then we can tell Excel to take a line of best fit, just be adding a trend line like so. I've already done that, so I'm just going to bring up the trend line information here. And, you know, assuming that this is a first order equation, first order rate, this should be a linear line. So a linear fit should be the best. And we can go down, and probably best to set it, force it to go through 0. Looks like I did not do that here, but we can simply set the intercept to 0, even if that reduces our error, you know, or increases our error a tiny bit. Truly, unless we have something else happening in the system, that's usually true. So anyway, then we can tell it to display the equation on the chart, check the r squared value out if we want, and then this equation then, y equals negative 0.3758x, that's our slope for this line, and we can take that slope and use it because that is literally our k star. So if we go back to our slides, what I have there is k star is equal to how that y changes divided by how x changes, right? So that is on our plot, that is y over x when plotted as a linear thing like this, right? So that slope then is just that number. We multiply it by -1, so that it gets rid of the negative. So that's really handy, and that would give us most of the way to our answer. So if k star then, so k star is equal to 0.3758. That means that's the same thing as k times c, which is k, which is what we're really looking for, times 1.8 milligrams per liter. Okay, so this is hopefully helping to show that difference between k star and k here. So then k, we could solve that and say k is going to be equal to this 0.3758 divided by 1.8. And that will give us our coefficient of specific lethality. And in fact, I think the question just asked for the rate constant of inactivation. So that's actually, we didn't have to go all the way to the specific lethality. This was just asking for the rate constant for the disinfection. That's a general term. That's actually our answer here. But we could go and take it, and by the way, this is per seconds. I should have included the time, the units there. Because our x-axis is in seconds, this has to be in seconds because it's some change that's unitless divided by the time in seconds. Okay, does that make sense? All right, so it turns out this is very helpful. We do this for all sorts of disinfection and chemical reactions, just a straightforward batch case, especially if you can have one of the reactants, let's say even if you're reacting 2 chemicals, if one of them stays approximately constant concentration, then you can just track the other and it's first order, and it's very nice that way. Any question? All right. So that brings us to UV disinfection. And essentially, it's going to act a lot lot like our regular disinfection, our chemical disinfection. It's just a bit fancier in a sense. We're shining light instead of using a chemical directly. So in our what's that?
I didn't know UV was subdivided.
Yes. So in our typical electromagnetic spectrum, you can think of all of these as some version of a photon, okay? And we understand from physics that that's something like a particle and something like a wave. And so we have some wave action happening, and we have a length, a wavelength, defined by the distance between two peaks. So that's what we would call lambda, our wavelength. Lambda. Okay, so based on how far apart these are, dictates a lot of stuff about how much energy the photon has and how it interacts with other matter. So if we take a very, very long wavelength, it's like very slowly waving up and down, that would be a pretty low energy. If we compare that with a really, really bouncy, energetic wavelength, a very short wavelength, that's a very highly energetic photon. And so the energy here means that if this photon hits something, it's going to impart a lot of energy if it's absorbed. If that energy is absorbed, if it doesn't just transmit through it or whatever, that's going to be a lot different than a very low energy photon. So we can think of it from our kind of visual senses. We have visible light that happens to be between about 400 nanometers to nearly 800 nanometers. Beyond that, we get infrared. Beyond infrared, we get, you know what I'll do is I'll move this over here so that it's a little bit better understood, maybe. Beyond infrared, we can get to radio waves and microwaves, probably micro first and then radio and all that. So other things we are familiar with in our environment, but we certainly can't see any of that, right? We don't really have senses that can tell us that there's infrared, aside from the fact that infrared would give some heating. There's enough energy in those photons that it tends to be absorbed, and it just causes a little more vibration of whatever molecules absorb it. So typically for infrared, it just imparts a little extra heat energy. Get into all sorts of vibrational relaxation and stuff like that. Generally, this is mostly just heat. In the visible spectrum, we have some other interesting things starting to happen, especially as we get down towards the lower ranges. You could have molecules that fluoresce, meaning they absorb the energy electronically. Their electrons literally gain an excitation, and then they drop back down to a ground state, and in doing so, they emit light of a different color. And it always goes from a higher energy to excite them, and then they sort of vibrate down a little. There's a little heat loss and stuff, and then they can emit a new photon and drop that energy back to normal and emit away a lower energy photon. So if you have a permanent marker, it's very likely that that's not a permanent marker, a highlighter. It's very likely that that's happening and helping it stand out a little brighter. And in fact, if you were to take a black light, like a UV light, in a dark room and shine it on a highlighter mark, you'll see very clearly that, oh, that's literally shining photons back out at me. And they are because you're using a UV light that you can't really see much with your own eyes, and it's striking that material, and that material is then absorbing it and emitting back out green or yellow or something. That's literally shining that light back out at you. Just rambling on photochemistry because that's kind of my research topic. When we go even further to the UV range, we can subdivide ultraviolet light into a few classifications. And if we take a look at sunlight, the amount of sunlight that reaches the surface of the Earth looks a little bit like this. And there's some wiggle room and stuff. But it looks about like that, in part because oxygen and ozone are absorbing a whole lot of ultraviolet light. It turns out that just about all of what we would call the germicidal or UVC light. Oops, germ. All the gremlin light. So all the germicidal light is basically absorbed and taken away by reactions in the atmosphere with ozone in the upper atmosphere and oxygen, and we're very happy about that because we would not like that to hit us because it can damage our DNA directly. The light that does arrive in the UV range is UVA or B, and a convenient way to talk about this type of light, this is the type of light it can contribute to sunburns, especially the UVB, but both have enough energy to cause excitations in a lot of different kinds of molecules, proteins and things, just what your body's made out of, your skin, your eyes, stuff inside your eyes, all that. There's enough energy there to excite a lot of electrons in random different molecules. And in addition to that whole fluorescence thing that some molecules can do, or some compounds, that excitation can make it more likely for whatever molecule that is to react with oxygen in the environment, just random oxygen. Oxygen likes to steal electrons. So if the electrons are already excited and ready to go, oxygen may be able to react with that chemical, that molecule, and oxidize it, taking away its electron and maybe sticking to it, bonding with it that way. So what I like to say for these guys is this is sort of the random acts of oxidation type of wavelength. Random acts. Not quite violence, although you maybe could look at it that way. Not quite kindness, probably, but oxidation. Now, some of that will happen with visible light. Just we're really getting into that higher energy there. We could, of course, go down further. Once you get below about 200, light just doesn't go anywhere through our atmosphere. You have to have a vacuum to get it to travel much, down until you get past where oxygen will absorb it. You can get to X-rays, which then pass through a lot of things. You don't want continuous X-rays because when something does absorb that energy, that could start causing damage. There's so much energy there. But small doses are common and not really a big deal. If you go down far enough, you get to like gamma rays and stuff, which kind of radiation stuff. All of the radiation is a form of photon. It's a type of electromagnetic spectrum stuff. It's just the super high energy, right? And as we see here, little changes in wavelength can actually change a lot what's happening in a photochemical sense. Okay, all that said, the germicidal is really what we care about for disinfection primarily, even if we can use that random acts of oxidation stuff to cause it, and we might be concerned about that for sunlight exposure. So what it would look like in practice then is having some way to deliver a lot of light continuously through water in a manner that the water is going to have pretty uniform and good contact with that light. So whatever reactor design we can make to achieve that is what we want to do. Conventionally, we've been pretty limited to fluorescent lights. A lot of my research is looking at using newly developed LEDs that can shine in that germicidal range, as that'll give us new abilities to design different types of reactors. But conventionally, we have these mercury vapor pressure lamps. So HG is mercury. And it turns out that mercury is, if you excite it with electricity in the right manner, it's going to fluoresce, thus a fluorescent lamp. Just like what I was saying a minute ago with the highlighter stuff, it's going to do that same highlighter thing, but it's going to fluoresce photons at germicidal wavelengths. And in fact, when we look at these are most likely LEDs kind of made to look like the standard fluorescent tubes. When we look at the standard fluorescent tubes, they're coated with a white frosted material, and that's going to capture all that UV and then fluoresce again and fluoresce it out as visible light. So those typical fluorescent bulbs in like office spaces and things. They have mercury in them, which is pretty toxic, mercury vapor even. So if you break them, you should probably clear the area for a little while, let that disperse, open the windows, whatever. Don't just chuck them in a dumpster and hang around chatting about the awful things you're doing to the environment by sending mercury everywhere. If every construction site dumped all their mercury into dumps, that would be bad, but breaking one lamp on accident is not such a big deal. Just don't want to inhale it directly, right? So, but the fluorescent lamps, just the standard ones, are a hazardous waste, just FYI, and is good to dispose of appropriately. So that's mercury vapor that is contained in a sealed vessel. We're going to excite electricity through it, and that's going to shine the UV light outwards. Now, typically when we do that, we actually want a second layer of protection because we really have to have a way to protect this bulb from the water. And we do that because we're going to have to clean it because it's going to get all gunked up with stuff. Okay, so typically we will have a sleeve around it, so a second casing, and the water is going to go through that. The light's going to travel through that, through the bulb itself and through the sleeve. Now the tricky part is, if we think back about our UV stuff, I was talking about how oxygen absorbs UVC, and this absorbs it, and that absorbs it. Almost everything absorbs UVC. It just, molecules like to, vibrate at that frequency, essentially. And so because of that, we have to be very fancy with materials to let it transmit through this glass. So normal glass does not work at all. It will just absorb all of the light. You won't be doing anything. So you have to use fancy quartz, basically. It's expensive and it's fragile. So then when these tubes get junked up by whatever organic matter is in the water and decides to react with these photons, they're absorbing a lot of photons, they're going to be extra reactive. You can get some mineral deposits, you can get the organic matter stuff. If you imagine like having a little bit of coffee, just put it on the table and let it dry out, right? And then you do it again. You'll see very quickly a buildup of some sort of scum. You'd have the same thing if you were just flowing coffee over a surface for a long time, especially if you have some weird photochemistry happening right there that could be adding to its propensity to react and stick to something. So it turns out that when we have water flowing across these systems, they do get fouled up, and then they're transmitting less light and therefore not working as well. So we have to clean them every so often. That means you have to physically open up the reactor, remove these things, and start scrubbing, typically, because it's stuck on there pretty hard. Inevitably, the things break sometimes, and then you've just broken a $1,000 quartz sleeve or something, and then you have to replace it, right? So these are not going to be cheap. They're going to be a lot more fragile than you'd like, and the cleaning is an issue. I have seen one innovation here that I'm showing kind of on the bottom, where if you have a new kind of material, you can afford a larger sleeve, then perhaps you could arrange the lights on the outside, shine them in, maybe a little better protection or handling for the lights themselves. And as I understand it, this was a polymer, so a plastic, that was able to transmit most of the light. That could potentially be a lot cheaper, maybe easier to clean or just to replace. It's not going to be as efficient as quartz in terms of transmitting the light through it, but there's some breakthroughs there. And we'll say transmittance, something like 70% of the light. So definitely not as efficient, but it might counteract in terms of the cost savings for cleaning and all of that. This is one of the interesting things about changing to LEDs. If we can change from specifically the germicidal wavelength that mercury gives us, that we've always been using, to something a little different, maybe we can let more light through with a cheaper material. So that's kind of one potential advantage. This is what it would look like inside a laboratory. Sometimes we use them to keep a microbial workspace clean or disinfected between things. With this window cover in front, you're pretty much completely safe against the UVC, but you would not want that running with your hands in it, right? And so most of these cabinets these days, as soon as you open it, it will turn off that lamp. It's also why you'll never get sunburned through your car windshields. Even if you take a very long road trip in a very hot, sunny car, you won't get sunburned unless you leave the windows open and you have your arms sticking out. Then you'll get a funny-looking sunburn where it cuts off right where that change happens, right? And that's in part by design. You know, we could design windshields that allow some of the UVA through, but basically they're all designed for against that. Okay, so I've been talking about this whole germicidal effectiveness thing and about light absorption by stuff. Here's a little more specific about what that looks like. So our low pressure mercury lamp, this would be a mercury lamp, it emits right about 254 nanometers. And that's just a standard emission based on mercury. And that gives us a good strong peak. And that's in this, if we call this UVC from about 200 to 280, if that's our UVC range, that's strongly in the UVC. And really the germicidal range is actually just based on where proteins absorb light in such a way where they can start reacting with each other and kind of not breaking down, but breaking down the DNA replication process. So if you can prevent the DNA replication by causing the proteins to react with themselves with the UV light, then you've got good disinfection. So the germicidal effectiveness curve here, as we'll see in a moment, is approximately the same thing as DNA adsorption, or absorption, excuse me. So where DNA is absorbing light, if I can, can't really talk and write too well at the same time here. If it's absorbing the light strongly, then we can recognize that that's going to kill it. Sometimes we use what's called medium pressure mercury lamps. Turns out that if we pressurize the system differently, we get a different emission. Sometimes this is useful for high intensity applications. Even though you're not getting as much direct UVC, apparently its energy efficiency is a little higher for certain cases. And then what you'll see here is that one, we do have plenty in the UVC range, but there's also a fair bit in the UVB and so on. Okay, so this would be light absorption by different organisms, and we see they're checking different wavelengths for this MS2 virus that I talked about earlier in that cryptosporidium we've discussed a little bit. And we see that that light absorption kind of follows that sort of germicidal curve, basically. So that's kind of what that's showing. And another way to look at it is, okay, relative to our standard 254 nanometer light, how effective in terms of a rate constant, how relatively effective are the different wavelengths. And so we see that if our standard 254, we define that as basically 1, well, we may be able to get some benefit for getting closer to 270. Once we're up around 300, we have almost no effectiveness. So just another way to kind of take a look at that. Okay, so how does the DNA damage work in the first place? Well, it's a lot like taking a zipper and putting a little drop of super glue on one side where two prongs are next to each other. Because then those two prongs are stuck together and there's no way that zipper is opening or closing anymore, right? Would be kind of a mean prank to do to somebody, but I suppose that could be a prank, right? So essentially what's happening is we've got these thymine-thymine dimers forming, dimer just meaning two molecules. And then the mer is like a unit or a molecule. basically we're taking these spots where there are two of these particular bases. If you go into biochemistry and kind of microbiology, you learn that there are base pairs in DNA, and there's several different types. And when particular ones of those, especially thymine, and I think there's a couple other combinations that are reactive in this manner, when they're next to each other, those particular spots can, if one of them absorbs the light, then it'll react with its neighbor, and then they'll fuse together and stick. So then that's kind of like the superglue. So then when some sort of an enzyme is coming along to splice the DNA to make a copy, it gets to that spot and it sticks and it can't do anything, right? It's like, can't function, can't pull it apart, can't work with it. Another way to take a look at that would be normal DNA on the left splitting and going about its business, and on the right it gets stopped where we have those thymine dimers. And the replication would stop there and not be able to proceed. Okay, I think what I'll do is I will stop here, and we'll finish off the UV conversation, talk a little bit about potential for UV repair afterwards next time.
I